let's take some time to look at permissions, file types, as well as various types of links, symbolic links, hard links, etc. So, file types, permissions, SymLinks. These are key components of organizing files throughout the Linux hierarchy. So features include the ability to protect files from unauthorized access. Also the ability to link to files in a variety of ways. And also a mechanism of classifying files. That is, of course, as we've mentioned, the leading bit which describes the type of file that you are involved with at any particular time. So a leading bit may include a hyphen, for example, which includes the fact that it is a standard file, such as a text file, binary file, otherwise media, rich media file, etc. So, first, let's explore file permissions. So our first task is to explore file permissions. How are file permissions handled within Linux? First, we should know that 10 bits are used to describe, and these are considered to be DAC or discretionary access controls, since the permissions that are associated with the file objects are solely at the discretion of the owner of the object, usually you as the root user or non-privileged users controlling access to their content. So it's solely at the discretion of the owner of the content, including root, of course. So 10 of these bits are used to describe permissions. Let's take a look at a sample file. We'll navigate into our home directory, and we're in as LinuxCBT2. So let's just go back to LinuxCBT, who has some files defined. So here's some files. We can pick any one from the list. Here's a leading file, and it is a normal file. One, it's colored black. Two, it has a leading bit, which is a hyphen or unfilled. So here's a sample file. When the leading bit is a hyphen, it means it's a normal file. It could be any type of file, PDF, document, rich media, text file, you name it. But it's a file. It's not a directory, nor a pipe, nor a character device, nor some other type of device. So leading hyphen, and if we just break this apart here, the first bit is leading hyphen, indicating the object. Remember, with computers we're dealing with subjects and objects. Subjects are users, objects are files. So leading hyphen indicating the object is a file, meaning that the bit is unfilled. Then we're left with these bits, RW hyphen, R hyphen hyphen, R hyphen hyphen, or 9 other bits, for a total of 10 bits. The bits are broken up, the following 9 bits are broken up into chunks of 3. So we see RW hyphen. These 3 bits correspond to the owner of the object. So correspond to the owner of the object. And we'll elaborate shortly some more. Followed by read hyphen hyphen, which corresponds to the group owner of the object. Let's just fix our English here. It actually corresponds to the owner. And the final 3 bits, which are flagged read hyphen hyphen as well, or R hyphen hyphen, they correspond, or this corresponds, we're grouping it, to everyone who has access to your system, whether remotely or locally. So everyone who has access to your system locally or remotely. So those are your 10 bits. Now, what does this all mean? Well, for a standard file, we look at the first set of bits, the 3 bits, and we see RW hyphen. Well, what are the possible bits? Well, the possible bits, or possible permissions that may be flagged on those bits include R for read, W for write, and X for, as you may have guessed, execute. None of these bits are flagged with X, so it doesn't come into play for this particular entry, but we'll pick out one momentarily, such as a directory, which certainly has X, otherwise we're not able to enter the directory, unless you're root, of course. So read, write, and execute. Read, of course, allows you to read the object. Write allows you to write and execute. In the event of a script, allows you to execute the script. In the event of a directory, it allows you to enter the directory. So enables script / binary execution or directory entry. That's where you'll find the execute bit in usage. And read and write are self-explanatory. Now, each of these permissions have various octal associations. Read is flagged with the value of 4. Write is flagged with 2. And execute is flagged with 1. So read, write, and execute when combined add up to make 7 for a total permission for that particular subject of 7. But they may be flagged in different ways, or the bits may be combined in different ways to achieve different numbers. For example, if you take a look at this first file, read and write are turned on, they're enabled, which means 4 plus 2 are enabled for a total permission set of 6. So for this file, what's really in place here between these bits is the value 6. That means, of course, that 6 really means read-write. So when using tools that influence permissions on objects such as files, 6 means read-write, 4 means read, 2 means write, but when combined, they mean read and write. And ditto for the next set of bits. So in the case of the group owner, we see simply read, which means obviously 4. And for everyone else, it's 4. This is where the common notation 644, octal notation of 644 comes into play to mean read or read, write, read, read. So 4, 2, and 1 are the permissions that we constantly play with in Nix-based environments to associate read, write, and execute privileges to objects for subjects or on behalf of subjects. If a bit is not enabled, it simply wears a hyphen. So in the case of this particular everyone else block, the 2 trailing bits are not enabled, so they have no values. Their values are effectively 0, if you will. So really, we should also include that hyphen basically means 0. So 0 permissions. And that's how we add the bits up. So when using tools, you can either reference the octal numerical notation or use the English translation of read, write, and execute when assigning permissions to various objects. Now, there are tools that allow us to influence these permissions, and there are also defaults that are in play that influence the permissions that are associated when objects are created. For example, if we echo the umask variable, let's just double check to see if it's set. In fact, let's just umask to see what's set. It's set to 0022. This influences permissions on directories and files away from the total permissions available. So let's just go ahead. The umask variable wasn't set. We normally have it set on our systems. In this case, it's not. Just as a quick reference for some of our scripts, it isn't set by default, by the way. So umask returns the default mask applied to the creation of new objects, of course by subjects, whether a process or a user. And our umask returned the following: 0022. Now this means that the permissions are subtracted from a total permission set. So let's just note subtracted from a total set of, or a total possible set of 0777. So when subtracted from 0777, this amounts to 0755. And this influences the creation of directories. So wherever umask 0022, and the leading 0 is ignored in this case, is in play, when directories are created, the directory is automatically flagged with 755. And to prove it, we're currently logged in as a Linux CBT. Let's make a directory umask test followed by an lsld. We need the D option to reveal the permissions of the directory as opposed to the contents of the directory. umask_test. Notice when we take this object after the system has applied the umask, we can analyze it and see that it's actually flagged 755, and that's because the umask is subtracted from the full or total mask set to derive the effective permissions. Notice also the leading bit in this case is D, which means directory. So in this case, D means directory. And in this case, also note that the permission set include RWX, which is 4 plus 2 plus 1, 7, R-X, which is 4 plus 1, 5, R-X, which is 4 plus 1, 5 for 755. These are the permissions that apply to directories when they're created when you have a umask of 0022. And similarly, when you create a new file, the files derive a slightly more restrictive umask on modern Linux systems of 644. So if we touch umask test file, for example, followed by an echo of the exit status and an LSL of umask_test dot or underscore file, we see that the permissions associated by default were 644. And that is because the file permissions that are derived from the umask setting are more restrictive. So let's just note that this reflects restrictive file creation umask application. So the effective permissions for creating files tend to be more strict than for creating directories to, for the most part, restrict the executability of files within the environment. So Linux inherently is not an execute-friendly environment for objects that are created. You have to elect to execute or assign an execute permission in order for the object to be able to execute. It doesn't normally or natively execute unless it's flagged by a process or by a subject at any given time. So 644 for files, let's just note directories normally are flagged 7 or 0755. We put the leading bit because it's used in some cases for certain features such as set GID, set UID. And files normally are flagged 0644. These are the permissions, the effective permissions that we work with. We should also note that there are some tools that allow us to impact the permissions, and we should discuss those. So permissions modification tools. They include, but are not limited to, change mod. Change mod changes the mode, the octal mode associated with an object, a file or a directory, for example. There's only 2 of the many types of objects supported. So changes the octal mode, and octal simply means base 8. So octal mode of object, which is usually, for most users, files and directories. For most users, of course. For super users or advanced users, it may also include devices that need to be created from time to time. So for example, let's see what may be of interest to us. Let's suppose that we've generated a new script file. So we're going to create a new script file, touch script1.shell sh. That'll be blank, it won't contain anything, but by default, as you may have come to imagine, this file will wear permissions of 644. So let's LSL script1.sh after we've created it. And this will give us the permissions momentarily. So let's paste this in over here. And notice it's flagged 6 read-write-44. Now if this is truly to be a script, we have to flag it executable. And that's where utilities like changemod or the GUI of GNOME come into play. So we've created the file, and we need to change mod from 644 to say 7 or perhaps some other permissions, but it needs to include the bit that allows you to execute, which has a value of 1. So if it's currently 644, it could become 755, for example. Now that depends, of course, on who you'd like to have execute this particular script. So let's change mod 755 script1.sh followed by an LSL of script1.sh. So now notice that it's colorized green to indicate that it's executable, despite the fact that the file is blank, so it contains no useful information, but nonetheless, from a file system perspective, the kernel sees this file as a file that may be executed, if and when we place some useful shell script code within. So it's 755, but what does this really mean? 755 now means that the owner, as well as the group owner, as well as everyone else, may execute the file, which may or may not be a good thing. And again, that's where change mod still becomes the tool of choice to help us achieve whatever nirvana we aspire towards. So read, write, execute means the owner of the object, LCBT, may execute the object. And that is indeed true. But the group owner may also execute the object, and anyone else may also execute the object. Anyone else who has access to the file may execute the object, which may be undesirable. So if this is not desirable, reduce the permission set to those who need to execute the object, supposing only the owner should be able to execute this object. So then we'll change from, instead of 755 script1.sh, we'll change it to something more restrictive. We don't want the others to be able to execute, so we'll make it 744. And this will be more restrictive. So let's change mod, and we'll just arrow key up and change 55 to 44. And now note, it's still flagged or colorized green, but only the owner, and of course root, there's always an exception for the user root, may execute the object. So if a member or a user is a member of the group LinuxCBT, they will not be able to execute the object. But if the user is indeed the user LinuxCBT, he or she will be able to execute this particular object at this particular time. So that's 744 permissions influencing the executability of the script. Now, how do we prove that this actually works? Well, to set up a script, first of all, you need to know the location of the shell. So if you echo your current shell, you'll see that we're running /bin bash. This needs to be placed at the header in a shebang header of the script. We can use an editor such as nano. So nano script1.sh and create a shebang header. And in it, we do something useful, such as echo, this is our script test. And there is our script. Nothing else to it. Perhaps we'll include a line that we used to or like to incorporate, and that's it. So now this is a script. It's no longer 0 bytes. Let's LSL script1.sh. It's now 53 bytes. Now, how do we execute this script? By default, Linux does not include the default or the current directory in its default path. So note, by default, Linux does not include the current directory in the path. So in order to execute a script that's in your current directory, you need to, so let's just execute script, reference the path using /. Dot means the current directory. So // and the name of the script, script1.sh, will do the trick. This will execute the script for us. So let's try to execute it, and you can just use tab completion to make it go quicker. And there it is, it's executed. This is our script test. You can do this as many times as you'd like. You can even put it into a loop. So for I in, as we've done before, sequence, let's say 10, do execute the script, done. And it does it 10 times. And you can alter this to whatever makes sense for your environment. So that script is now executable. But the script is not executable by another user. For example, supposing we copied the script to a different user's account or provided access to the script from our account. For example, let's LSLD our home directory to see what the privileges are currently. So this tells us that anyone may enter the LinuxCBT directory. How about the temp directory? LSLD temp, ditto for temp. So that means if we're in another shell, and we'll drop from the remote system. We no longer need connectivity to that system at this time. And let's open a new shell and sun as LinuxCBT2. This will prompt us for the password, and so long as we authenticate, we'll be able to connect into our home directory. So now we're in as LinuxCBT2. This is the default setup. To execute the script that belongs to the user LinuxCBT, we'll simply reference LinuxCBT temp script1.sh. Notice, it doesn't allow us to. How about our ability to enumerate the fact that the script lives? We can see the script. We can even read the contents of the script. Let's cat the contents. Since it's short, we don't need a pager. So we can actually see what the script does, but we may not execute the script. It doesn't allow us to. Even if we use, let's say, the absolute path, home LinuxCBT, it will not work because we do not have execute permissions. As it currently stands, if we execute ID as LinuxCBT2, we belong to a GID of LinuxCBT2. That's the sole group. We do not belong to the group LinuxCBT. So we are classified as everyone else, or the last few bits, 7, 8, and 9, or 8, 9, and 10, depending on how you count, whether or not you base your counting from 0 or 1. So we fall into these last 3 bits for which we may not execute. Now, if we change the permissions, the user will be able to execute the script. So allow other users, meaning everyone else, to execute the script. And that's quite simple. So change mod as the owner or as root. We had 744, but this time we probably need 745 script1.sh because it will allow the last group to execute, but not the group LinuxCBT, which is okay because no other user on the system currently belongs to the group LinuxCBT. Let's echo the exit status. Let's LSL script1sh, and now it's set to 745. And in fact, if we stat the file, we'll see the representation octally 745 translated to its English notation. So now let's try to execute the script. That's the FQDN. Now let's also do it using tilde interpolation, and it works. And as soon as we drop the privilege, it goes away. So let's change it to 744, and we'll follow that up if it works with a stat of script1sh, and it's set to 744. And now when we try to execute the script again, it fails, as it should. So that's how you flag permissions on a particular item to influence whether or not it may be executed or even read. For example, you can drop read permissions. So to drop read, just change mod, let's say, from 744 to 740 script1.sh, and then when the user tries to read the file using our recently executed command of cat, now it fails. We can confirm the fact that the script exists, so LinuxCBT, and this will be temp script1.sh, but we may not read the file, so 740 prevents the user from reading the file. Now, there are English translated ways or symbolic ways of representing these octal permissions, using U, for example, G, for example, or O, for example, to influence the ownership permission, or A as a shortcut to indicate all. So supposing, for example, we wanted to set execute permissions on this file, we could, let's go ahead and indicate change mod using the symbolic notation U plus X script1.sh. So let's go ahead and just quote this out, and let's take a look at the current permission set. It should be set to 740. We'll stat it, and it is. So when we look at script1.sh, it's still flagged as executable for the owner. But now if we change mod U plus X script1.sh followed by an LSL of script1.sh, notice what it's set to. Same permissions, because the U influences the owner of the object. So it was flagged that. So if we change mod, for example, let's say 644 script1.sh, and now let's LSL it. It's 644. It's no longer executable. And if we influence it with U plus X, it turns on for the owner of the object executability. So this is equivalent to flagging the file executable for the owner. So allows owner to execute the file. And symbolically, we may also turn on for the group, for example, so G plus X. And you can also combine this with minus as well to remove permissions on the converse. So let's change mod G plus X, and you have to do this as owner or root. Script1sh followed by an LSL, script1sh, and now note that anyone who belongs to the group LinuxCBT may execute, and this influences the group, so allows group owner to execute the file. And of course, the last section would be O plus X, script1.sh. And this allows everyone else to execute the file. So let's change mod, let's just change G to O, and now all of a sudden everyone can execute this file. And of course, to confirm it as the user LinuxCBT2, let's try to execute the script, and indeed it executes. So that means anyone else who has access to the file itself may execute the script. Of course, that means directory permissions above must allow access to the file. If you want to use the symbolic notation or the English or whatever language to remove permissions, let's say removing from everyone else, we could do O minus X, and now that permission has been dropped. We can do O, let's say minus R, and that takes off the read permission. And we can pick apart these permissions as we see fit using symbolic notation. So both notations are supported, symbolic and octal. I use octal because it's simply faster and more accustomed to it. But nonetheless, it's available as a means of flagging permissions on your objects using change mod. Now, these files that are created are by default owned by the user who created the file, but there are times when you need to change the ownership of a file to someone else for various reasons. Let's say directories that are shared where you need to ensure that a particular subject owns the object. So object ownership. And two utilities come to mind, including change ownership and change group, which allows you to change the group ownership of a particular object. So currently script1.sh is owned by LinuxCBT, and we can change that to LinuxCBT2, for example, script1.sh. And then that user will own the file. But overriding permissions or permissions that are higher up, directory permissions, flow downwards. So if the user doesn't have access to modify contents of a directory, they will not be able to change the file. So let's take a look. We'll LSL script1sh as a result. And notice, this gave us an ownership change problem because we are the owner, but we cannot change to another non-privileged user. So the way to work around this is to make the change as the user LinuxCBT, or as the user root, that is. So let's find a root shell. And once in, we'll execute the same command, script1sh. Now let's LSL script1sh, and now note that it's owned by LinuxCBT2. The user has full privileges to it. But it begs the question, can the user enter the other user's home directory to make changes? So let's SU in as LinuxCBT2, and now we're in that directory as LinuxCBT2. So we're in LinuxCBT's directory as LinuxCBT2. Let's see whether or not we can modify script1.sh. Let's try to echo something else. LinuxCBT2. Save the changes, and notice script1.sh has been updated. So what this tells us is if we look at the permissions associated with the temp directory above, we're able to read and execute the directory. But because we have exclusive ownership on the file, we're able to make changes to the file. So we're able to make the change to this file in this case. But if, let's say, for example, the user was not able to enter the directory temp, then they would not be able to make changes to the file because of the downward permissions flowing, preventing the user from making changes to the file accordingly. So chown makes that change. But there are times when you need to just change the group associated with the file. So change group will help you out. So supposing you wanted to change the group also to LinuxCBT2, this is an option. So changes the group ownership of the file, whereas this changes the user ownership of the file. And change group does that for us. Again, you do it as the owner of the object. So let's try to change group. We're now logged in as LinuxCBT2. The group owner is LinuxCBT. Let's try to change group LinuxCBT to script1.sh. And because we own the file, we're able to do so. So it's been changed. But before we didn't, so we were not able to go from one non-privileged user to another. But we can always claim ownership if we outright own the file. So in that case, it worked. And chown will allow you to change both user and group ownership permissions in one execution by using a colon as a terminator, as we've already shown you. So that's a little bit on chown, as well as change group, as well as change mod for influencing permissions that are on various files. Now quickly, let's take a look at symbolic links. So for symbolic links, and we should just note that two types exist, and they include soft and hard. Now, a soft link is basically a shortcut in the sense of how we think about shortcuts in the Windows context. So a shortcut simply means that you alias a file, you don't actually create or reference the underlying blocks. You simply have a topical representation to the file. That's what a shortcut really is, and that's a soft link. So if a target file is, let's say, 6 megabytes, its symlink will be very small, a very small fraction of that, as it's just a pointer to the target file. Whereas a hard link is really a pointer to the underlying blocks which hold the file. So it doesn't copy the file, but it creates another outstanding reference for the file. So creates another outstanding reference to the underlying disk blocks, really to the inodes from a file system perspective. The inodes organize the disk blocks. And we should also note that soft or symbolic links can traverse file systems, but we should note that may not, these are hard links, traverse file systems. And as we've mentioned through various Linux CBT editions, this is straightforward because of the fact that each operating system's file systems maintains a list of inodes associated with that particular file system, and the numbers are reused. So that's why hard links may not traverse file systems. So to create a symlink, let's see how this would work. Well, we have script1.sh, which is owned by Linux CBT 2 now, but it resides in the user Linux CBT temp, Linux CBT's home directory /temp. So how do we create a link to this file so that we have access to it? Well, one way is to create a soft link. So let's navigate into our home directory. Supposing as a user Linux CBT 2, we have a directory called scripts. And that's where we'd like to reference our scripts, because that's how the user Linux CBT2 works. Using ln with the S option to indicate that it's a soft link, followed by the source, then the target will create the link. So B, create soft links. So B1 would be ln s tilde Linux CBT temp script1.sh. With no target, the same file name is used in the target. But you can influence that by changing the target to something else. So a shortcut or a symlink can be named anything. But if you don't, then it simply just uses the source name. Now let's echo the exit status. And now you're going to see that we have a link which shows an arrow pointing to the true destination or the true location of the source file. This now means that as a user Linux CBT2, so long as our privileges, our underlying privileges on the file are intact, we can go ahead and interact with the file, either executing it, modifying it, let's say making a change, post symlink, and so on. So long as our permissions are intact, we can interact with this shortcut, which really points to the other directory owned by some other user, Linux CBT in this case. That's a soft link. We can also link using a different name. So for example, lns, and this time instead of calling it script1.sh, let's call it script.sh. And now we have a link script.sh. It's important to note that the counters associated with the source file do not increase as a result of creating soft links. So as a user Linux CBT, for example, let's take a look at script1.sh, notice that script1.sh has one link, and that's this. This is the only incarnation of the file which points to the underlying inodes. Hard links, however, increase this counter. So this counter that you see here really reflects hard links, not soft links. And that becomes very important because as the file is manipulated, removed, and so on, the file system has to keep track of how many outstanding references exist before it allows the file to be entirely deleted from the underlying storage blocks. So here are two incarnations, and they can execute by using either name and can be manipulated in either case. So let's go ahead and make this post SymLink and new link. Save the changes. Then when you cat either file, it's updated accordingly. So this is exactly what we expect with a SymLink. And again, a SymLink can traverse file systems. So this is a root file system. We don't have another file system in place currently, but at some point when we do, we'll show you how that works. Now hard links, again, increase the counters associated with the file. So C create hard links. So C1, for example. Simple invocation, don't use the S option, just omit the S option. So now we'll reference Linux CBT, temp, script1.sh, and it's the same syntax. So you determine what the target name is to be. Hard links can wear any number of names because what's really being referenced is the underlying storage blocks. So let's find ln from our history. Here's a link to ln. Let's drop the S option. And notice it already exists, script.sh. So let's call this script hard sh. Echo the exit status, and now let's LSL. And now note that script hard.sh has an increased counter of 1 to 2, which means as you manipulate this file through various places in your file system, the counter will be incremented or decremented. Stat will also reflect this. So stat script_hard.sh also reflects the number of links. These are hard links to the file. And this file is occupying, as you can see, 4096. Although the file is only 98 bytes, but it occupies 4096, 8 blocks, which means 512 bytes per block. And that's why it's taking up so much space. So this disk is organized into 4K chunks, ostensibly. So this file now has 2 links. What does that mean? Well, if we remove the file, let's say from the source directory, and we don't have the privileges anymore, but let's try to do it, show you what would happen. And let's echo the exit status. Let's see if script1.sh, actually let us remove it because we own the directory and there's still another object existing. So we do have permissions to do it. Note what happens. One, the hard links has been, or hard link has been decremented by 1. And 2, both of the symbolic links have broken. And that's because we've removed the source file. Symbolic links, soft symbolic links, are truly like shortcuts. If you remove the source file, the shortcuts or soft symbolic links break. But hard links are different. The file still exists here. We can execute it accordingly. Now we can easily fix this problem. We can remove these links and create new links to the hard or to the actual representation on the file system. So let's remove rf script1.sh and script.sh. That cleans up the broken links. And it's colorized red with a black backdrop to indicate to us that there's a problem. It would no longer execute. And by the way, it would fail to execute. And now we can create a soft link, but that would obviate the need, or we have now obviated the need to do so because we have script_hard.sh in this directory, but you can if you'd like. So script_hard.sh, let's link it to script1.sh. Now we have a new soft link. Now if you change the name of this file, move script_hard.sh, so let's say simply script.sh, all of a sudden you've broken the symbolic link again. And if you try to execute the symbolic link, the tab completion doesn't even reference it. It doesn't work. So you'll have to remove it. There isn't a modify per se for the symbolic link. You simply remove it and then recreate it to fix that issue. So hard links may not traverse file systems and increment the reference, hard links reference or links reference by 1 for each outstanding. You can link them all over. It doesn't duplicate the storage. It simply creates entries in the file system to indicate that the file is being referenced in more than one place. It's a powerful concept. Soft links work just like shortcuts. It allows you to create a link across file systems or within file systems to data that exists anywhere, so long as you have permissions, of course. We should just note that symbolic links are governed by their underlying or by the file's underlying permissions. This is always the case. That never changes. So that's a little bit about Linux file permissions. We've touched on read, write, execute, the number of bits used. We've discussed a few file types, including standard files, directories, for example. We've also talked about the symbolic representation, the octal representation, SymLinks, both soft and hard. And that's how you effect permissions throughout your environment. The standard permission set in Linux is rather restrictive and makes the environment rather secure. So let's move on to some other items.